So this is the last lecture of the school, and I would like to thank the organizer, especially Leo, for giving me this opportunity to talk about something that's quite exotic. So I know that it has been a long 4 weeks for most of you, and I cannot understand how I could have listened to 3 lectures a day for the whole 4 weeks. Yeah, for the last few days I have been listening, and it was already hard. Given that I have to listen only to two lectures a day instead of 3, that's already hard. So let's try to finish what let's try to I want to do something useful today. At least I think when we do physics, it's always reward. It's always a reward to derive something concrete. I hope to derive something result that is concrete today. But I have to remind you first about the previous lecture. So we look at the quantum Hall liquid in a slightly semi-classical point of view, that it's collections of at the lowest Landau level. In the lowest Landau level regimes, the only coordinates that are important are the guiding center coordinates. So from the point of view of classical mechanics, we have a system whose Hamiltonian is just the potential energy. The kinetic energy in fractional quantum Hall effect completely goes away. So this problem is non-trivial because these guiding center coordinates are like x and p in phase space. So it's like a gas of particle living in phase space, and that's make the problem quite difficult to solve. So then last time we talked about an exotic set of conservation laws that are all follows from an equation, continuity equation that symbolically I wrote in this way. There are these indices in this second term that I derived in the previous lecture, but then we derived the conservation of some exotic conservation laws, like conservation of dipole moment, conservation of these things that looks like moment of inertia. So these things are very similar, very familiar to people who are doing fractal physics. And then we say that this symmetry can be realized as a gauge, can be put in correspondence with the higher rank gauge symmetry, namely our system. If our system can be coupled to a set of gauge field, in this case a scalar and a tensor field, in such a way that there is a gauge symmetry of a form that's quite different from the usual gauge symmetry, because these the scalar component transform like usual scalar components lambda dot, but here the transformation has 2 special derivative instead of 1. So if that is the case, we say then we would have the conservation, the continuity equation at that time. Today I want to put this point together, namely I want to demonstrate that the dynamics of this basically even at the classical level, we can see that the dynamics of the guiding center coordinates can be coupled to this set of gauge field in such a way that we see this gauge symmetry, and then that will at least convince us that this is a real symmetry of the lowest Landau level problem.
So the continuity, this high order continuity equation, you derived it in a sum approximation from the conservation of momentum and conservation of charge, ignoring some terms. So in the classical limits, it's only exact, like in some omega or k goes to 0 limit.
It's a limit in which you have, if you remember, it's a limit when the frequency under consideration is much less than the cyclotron frequency. That's exactly the limit in which you can ignore everything except the guiding center coordinate. So these are written in the same limit. Yeah, and so I'm going to demonstrate that these things, the symmetry can be implemented at the level of the classical dynamics of the guiding center.
But okay, good, that helps. But maybe a related question is, so the first line is kind of a microscopic Hamiltonian limit, but the continuity equation written for these effective degrees of freedom. Can you rewrite the microscopic Hamiltonian where it's obvious that it has maybe microscopic degrees of freedom coupled to some Haber-Strange field or some long wavelength fields like rho and t?
No, this equation is not a long wavelength equation. Exact conservation law.
If I take rho to be a delta
some of delta function, then you can define the.
T just comes out as.
You have to compute what this t is. Yeah, so it's not that trivial because when you compute rho dot, you differentiate and you get this derivative of v, and then you have to convince yourself that this all can be written this way. And the way that I'm going to do now probably is more direct, more easier technically. The way that is can be easier.
Valid independent of the form of v. It only depends on the fact that there's a quotient bracket between different components of R. That has a C number. That's the constant. That's the only thing that matters.
That's the only thing that matters. So the precise form of T depends on V. The precise form of rho is just sum of delta functions. Doesn't
but the
know
two derivatives come from those quotient brackets.
From this, yeah. Okay, so we are going to try to relate these points together, and let me make a first prelude in which we remind ourselves of a classical mechanics notion of canonical transformation. So it is purely classical mechanics. It's sometimes you learn this closer to the end of theoretical of the classical mechanics course. Sometimes not at all. If the course is short, then there is no time to do this stuff. But it's typically in the textbook.
Old 1950 textbook.
Or Landau Lipschitz. Yeah. But I don't know if the Goldstein third edition. Yeah, Goldstein has a next edition. I don't know if it's there. Yeah. Hopefully it's there. Okay, so what is the canonical transformation? So in classical mechanics, usually we define the phase space as Q and P. But I'm going to, with a view on the problem at hand, I'm going to define the phase space, my space to be a space of Rx and Ry. I'm going to consider in this board only a single particle problem, one particle with guiding center coordinate Rx, Ry, and last time we said that this Poisson brackets is equal, I think, minus LB squared, a magnetic length squared. So we have phase space, so you can think about this as P and Q. Oh, the canonical transformation is a transformation from, say, Ri to another coordinate, let me call that R prime, Ri prime, which are functions of Ri. So each of these two R prime is a function of two variable in such a way, and it is the canonical transformation if the Poisson brackets between the prime coordinates would be the same. Now we know that for any pair of functions, a phase space, we can define the Poisson bracket. So this is just give us some equations that these functions have to satisfy in order for that to be a canonical transformation.
For some bracketing here means like drx from the R.
Yeah, so it's drx prime over drx, dry prime over dry minus rx y prime equals the same thing as before. So if that is the case, then these two coordinates will still be, can be sometimes considered as canonically conjugate variable. Yeah. No, here is just one particle. So I have one particle. Is that your? Yeah. So Rx and Ry. Each of these. So Rx prime is a function of Rx and Ry.
That's why it's canonical.
It makes it P and in Q. And there are, yeah, P and Q. Yeah, it makes it P and Q. Okay, so now I want to simplify this a bit and think about infinitesimal canonical transformation. It's similar to the approach in Lie group when sometimes it's easier to think about elements of Lie group that's near unity, and then reduce the problem to problem of Lie algebra. So one can check that the following transformation is a canonical transformation. So I'm going to suppress the index I. R prime equal to R plus the Poisson brackets of R with any functions of R. So infinitesimal means here you think about this lambda as something very small. That's right. Lambda much smaller than 1, a little bit smaller than something. So that this second term is in some sense small compared to this first term. So this is as an exercise, you can check that the Poisson bracket between these two Rx prime, Ry prime is the same as the Poisson bracket between R and R. But there is another way to think about this. Right? This is, remember that if you have a system, a dynamical system governed by a Hamiltonian R, H as a function of R, then the dynamics is governed by these equations. R dot equals the Poisson bracket of H and R. So what I'm writing here is just a small infinitesimal time evolution under the influence of a Hamiltonian, which is lambda. And the statement that you can also find in textbook is that Hamiltonian evolution generate canonical transformation. If you have two P and Q, at later time, these two P and Q would still have unit Poisson bracket. So what it's here is just canonical, small canonical transformation. Okay, so now let me ask the following question. Suppose so lambda is now this equation can be thought of as some time evolution with a Hamiltonian playing, that lambda plays the role of the Hamiltonian. in a unit, in a small step. Okay, so now let's forget about this. Think about this is let's think about the real problem with the real Hamiltonian. Let's say we have some system with the Hamiltonian H, and the equation of motion for R is given by this. And suppose we define R prime to be then this R plus R of lambda of R. So this R prime, of course, is then again a function of R. Then the question is, what equations does R prime satisfy? So this is also another thing that in textbook you can see, you can find, but the answer is going to be rather trivial. But the not trivial question is the following: suppose now our lambda is not a function of R, but also a function of time. That means we are doing canonical transformation on R. So this R prime is related to R, but the relation changes with time. Then what equation does R prime satisfy? Okay, so I want to take a look at this problem. So going back to doing classical mechanics, I have R prime, okay, equal. So I'm going to do things pretty explicitly here. A lot of the details in the inside will be redundant, but it's good to just make sure everything works. So R prime is equal to R plus R and then lambda, but now lambda is a function of R and T. So I'm going to differentiate this R prime with respect to time to try to think what this is. So R prime, when I differentiate with respect to time, I have R dot. And here there are various places where derivative with respect to time can hit this R, can hit this R because this R is a function of time, and can also hit this T. So there are three terms. One is, so I'm going to write this way, R and H. R and H because that, and then the lambda. So I'm going to suppress the argument. So all the arguments here on the right side supposed to be R. And then I have R lambda H. That is what happened if I hit this R. Time evolution of any function of R is the Poisson bracket with the Hamiltonian. And then I have R and then lambda dot. Lambda dot is also some function of R, and so you can define that Poisson bracket. Okay, so that's what we have. Now let's do this calculation. Okay, so there is a Bianchi identity that, or Jacobi identity, that allow us to combine these two terms. I think that's going to be something like R lambda, right? And then H. I think it's going to be something like that. So let me write this r prime is equal to r dot plus that and then plus r lambda dot. Then see, this r dot can be written as the commutator of r with h. And so from here, you see the commutator of r prime at h. So that's nothing very surprising. The surprise thing is that we have, well, at the end, we have r and lambda prime. But let me write this way, r prime delta dot plus o of lambda squared. That's because r prime and r differ from each other, but only by an amount equal to lambda. So I can replace that r here with r prime. And so the result of this calculation is that the time evolution of my r prime can be written as the commutator of r prime with a new Hamiltonian h prime, which is h plus lambda dot. Okay, so in classical mechanics, one usually make the statement that the canonical transformation, when you do canonical transformation, you don't have to change the Hamiltonian. You just use the old Hamiltonian. So here, if what we have found slightly beyond what is written in textbook is that if the canonical transformation is time dependent, then we have to modify the Hamiltonian by an amount just equal to the time derivative of that lambda that it's. Now, when we write this r prime and h, right, prime, we can think about this as taking derivative. In all this calculation, we say that the inside is a function of r, and so this we have been thinking about that as this Poisson bracket, but there is no. We don't have to do that. We can also use r prime to do the Poisson bracket. You can think about this h prime as a function of the new coordinate. So we can write the following: h prime of r prime is h of r, right, plus lambda dot of r. When you think about this r as functions of r prime, it's just the Poisson brackets of the new r and Poisson brackets of the old r are all canonical, so it doesn't matter. We can use either coordinate to system of coordinates to write the equation of motion. And so the result is the following. So to summarize, under canonical transformation, if the canonical transformation is time independent, then the Hamiltonian is preserved. We just need to rewrite the Hamiltonian in terms of the new coordinates. So whatever you have before, like p squared plus q squared, and you have to re-express this p and q in terms of the new canonical coordinate and have a new Hamiltonian, and that can use that. But if the canonical transformation is time dependent, then there is a new contribution to the Hamiltonian proportional to the derivative of that, how fast the canonical transformation changes with time. Any question so far?
There's an assumption that the transformation is invertible here. Is that going to be a significant restriction?
So here I'm doing, strictly speaking, only canonical, this infinitesimal transformation. So you can either go back and forth with the, but I thought all canonical transformation are invertible, no? If the phase, yeah, I have to think, but maybe not globally, right? Maybe only locally in some place. Yeah.
preserving. Invariant preserving is the same thing with the commutation, Poisson bracket preserving.
Yeah, so what, so yeah,
Preservation of that Poisson bracket.
so Poisson bracket, if you think about this expression, it basically says that the Jacobian of the transformation of Rx, Ry to Rx prime, Ri prime is 1. Jacobian is 1 means that the area is preserved. Right, like it's natural. Yeah. Okay, so I'm going to use that, and I'm going to try to see what that canonical transformation is going to do to my system of guiding center coordinate in the quantum Hall problem. Can I? What I do is I'm going to start with this with the Hamiltonian, and then do a canonical transformation and see whether I get back the same Hamiltonian or not. Do I get the symmetry that I want or not? So I have, let me try. Now I'm going to a slightly more complicated many body problem, just slightly more complicated. So I have Hamiltonian equals sum over A and B, right? Some potential. So for concreteness, let me write down just the Coulomb potential minus RB, sum over this Coulomb potential, but any potential is fine. Plus, I'm going to include here the potential phi. So I put the system in an external potential phi, and then each particle contribute phi at the position of that particle to the Hamiltonian. Okay. So now I'm going to do the following. I'm going to do canonical transformation. But I'm going to do the same canonical transformation for all particles. Yeah, so each of these particles live in its own phase space, two-dimensional space. I'm going to do the same canonical transformation for all of these. So I have R A going to R A prime equal R A plus R A lambda. Okay, so lambda R A. This is only one function for all R. Whatever this function is, yeah, going to just use what the same function to do a canonical transformation for all the particles. So in the quantum system, that's necessary because of all the particles are indistinguishable, and so it's impossible to do different canonical transformations for different particles. So once you do this canonical transformation, we know that R prime, R A prime dot is going to be governed by a Hamiltonian equation with a new Hamiltonian, H prime, right? And then this H prime is going to be the following. So H prime is going to be a sum over E squared over. Now, this has to be R, but R is now a function of R prime. So let me write this way. B squared, right? Plus sum over phi of R A. And then there is this extra term lambda dot. So each of the canonical transformation give me an extra lambda dot. So I'm going to do just lambda dot of RA. Yeah.
You don't want a square.
Yeah, there is no square. I'm sorry. But I'm what I'm seeing here is that So let's look at the first term first. This term. Previously, before canonical transformation, we had a system of particles interacting with each other through a Coulomb potential, whose potential depends on the distance, inversely proportional to the distance between the particle. But now, what happened is that the potential now written in terms of the new variable is no longer Coulomb potential. Some kind of a different type of potential. So let me draw a picture. Maybe draw a picture. Yeah. So this is my old coordinate. So it's like Rx, Ry. So here Rx goes this way, Ry goes this way. But what I've done is a canonical transformation. So my new system of coordinates are slightly different from the old. There's something like this. The line of constant Rx prime and Ry prime is no longer coincide with the old system, but I'm still forced to compute my potential using the old coordinate. So the Hamiltonian, strictly speaking, this Hamiltonian is the two-body interaction part is not the same as before. So taking this Hamilton, we can define the canonical transformation, but the Hamiltonian does not preserve the form of this. These are general, not still not the symmetry of our problem of the Hamiltonian. In other words, Hamiltonian do not commute with this general canonical transformation. Okay, but this is the situation similar to the situation in the scalar field theory that we have talked about last time. A gauge transformation in the scalar field theory can be a symmetry if we couple that complex scalar field to a gauge field. So now I have to think, how do I couple this system to gauge field so that I can simultaneously change the gauge potential and some kind of a gauge field. If I simultaneously, let me say it this way, I can preserve the form of the Hamiltonian by allowing the external potential to transform as well. So does it make sense?
You're going to adjust phi.
Yeah. So this one actually is the we already see one component of that here. This phi becomes this. So what I have to declare is that under transformation, phi goes to phi plus lambda dot. So this Hamiltonian is just equal to the old Hamiltonian with in the new. Well, yeah, that's how the Hamiltonian.
Can you clarify? So even without this gauge field, so to speak, that gauge field allows you to preserve the form R and R prime. But even without it, the new Hamiltonian H prime is the governing Hamiltonian for evolution of R prime.
It is a different Hamiltonian.
Different.
Yeah. So it's a different Hamiltonian. So if you want to preserve the form of the equation of motion, so let's see what happened in the case of complex scalar field that are more familiar, right? I can say my equation of motion is this m squared phi, or let's do massless scalar field equal to 0. Now, if I define phi prime equal phi times e to the I alpha, okay, the equation of motion is no longer this. It's more complicated equation like d mu square phi minus I alpha, d mu alpha, d mu phi, maybe it says some other term equal to 0. So phi prime doesn't satisfy the same equation. But what is useful in field theory is that we can pretend that we have a gauge field what happened is that if we now do this equation with a gauge field, we couple the theory with the gauge field, we can preserve the gauge symmetry. So yeah, and that gauge field is useful because we can differentiate the action with respect to gauge field and get the current, and then do all kind of things with the gauge field.
It's just convenient because, you know, the fact that Hamilton doesn't preserve the form, so what? Like, you know.
So what happened here is the following: you have the Hamiltonian, the system has a gauge, has a set of conserved current, and the fact that there's conserved current allows us to couple it to gauge field like A mu J mu, and so that the system has gauge invariant. Yeah. If we didn't have this conserved current, then we wouldn't be able to do that. So it's a way to formalize the notion of conserved current and continuity equation, etc. to make. Yeah, so I can call this H prime to be a new phi prime, for example. So my phi go to phi prime equal to that. So that would take care of this part. I would say that this phi is some gauge field that transform under canonical transformation in this way. But I still have to do something with this. And it's clear now what we're going to do with this. We have to define distance not with respect to the flat metric, but with respect to a general metric. So let's imagine that we put our quantum Hall system on a curved manifold with some metric GIJR, and that is where our problem is different from the usual quantum mechanics in phase space. Phase space usually doesn't know, there is no notion of metric in phase space, but in the case of the quantum Hall problem, since these are real coordinates of the center of this small orbit, the Coulomb potential knows about real distance between 2 points in that phase space, and so we need to define the metric. But this metric, in principle, at the theoretical level, can be anything. So we can write this H, and now this H depends on not only on R, but only also on two set of gauge field phi of R. So let me write this way: sum over AB E square over. Instead of that, I'm going to define some distance. Let me call that D, a distance between the point RA and point RB. And that distance is a distance on this curved manifold from point XA to point RA to point RB. So I have to draw some kind of a geodesic line between these two, compute its distance, and then put it in the Hamiltonian. So this distance knows about G, knows about this metric. Then I have sum over phi of RA. So the Hamiltonian, we pretend that we have some way to couple our quantum Hall problem with the external potential phi and an external metric. Now, external phi is very easy to imagine being able to do that. Just stick some gate to the quantum Hall problem, and you can imagine changing the potential for this particle. For metric, to change metric, it's more theoretical things now. Unless you have a neutron star somewhere that you can stick to the problem. So, but let's think about that from a purely theoretical point of view. As a trick to expose symmetries of the system.
Point of view of a real sample, right? If voltage changes underneath the sample, that'll effectively change the field.
You can try to somehow make the put in gates, and then it's not going to be exact, but we can mimic something like that. Yeah, like if you put a substrate with the spatially dependent dielectric constant, for example, that we can imagine this to happen.
So that's one way of viewing it. I thought the other way of viewing it is, metric is just a geometrical way of accounting that a description of a distance is not, sum of squares, simple sum of squares. That's another way.
Mhm.
Isn't that just another,
I'm just trying to see how I can realize a quantum Hall problem with an arbitrary metric, and that's I imagine changing the Coulomb potential to fit it into this form.
But what I'm trying to say is that distance with a metric.
Yeah, this distance is no longer, this distance is no longer different of sum of square, but it's rather integral over a geodesics of like Gij of R, dr I over ds, dr over ds. I think it's square root, right? Where it's a boundary condition that R s goes from 0 to 1, and then R of 0 is Ra, R of 1 is Rb. And also we need to minimize this distance among all the curves. So that would be this distance. So it's implicitly defined, but one can imagine computing it for G that slightly deviate from delta Ij, for example, and get some explicit form that I'm not writing down here. It's going to be like 1 divided by Ra square plus Ra minus Rb square plus some correction of order Hij, which can be computed explicitly. Mhm.
It's sum of squares.
Yeah.
But in terms of written in terms of our primes, it's not a sum of squares of our primes.
Yeah.
Some nonlinear thing.
Yeah.
But you can think of that not sum of squares in terms of our prime as the
Yeah. Here I'm doing slightly something different. I'm going to make R in R prime democratic, so that they.
No, that's what I'm right. That's
yeah.
that's
I'm just doing. I'm just saying even R in terms of R, the notion of distance is not 1 over sum of R squared.
You make it covariant.
Yeah. So that any system of coordinates, there's nothing single out. Just make it to make things simpler. Of course, physically, in a physical system, there is a
That's what I'm saying.
single out.
R is the physical coordinates of the physical, sample,
Mm-hmm.
and it has a metric, and that metric is flat.
Mm-hmm. Mm-hmm.
But then, when written in terms of R prime, it looks like you have a non-flat metric.
Yeah, but I'm not an experimentalist, so you can imagine. Well, I live in a curved space. Yeah, and then every system of coordinate is the same. Now, when I derive a lot of results, but at the end, when I have, for example, some continuity equation, at the end, I put my metric in flat, and then get the physical result.
There's a special samples coordinate system.
Yeah.
And there it's flat in the sum of squares. All the other ones have a coordinate transform metric, generalized coordinate transform metric.
Which can be curved. Which doesn't have to be my system can live on a sphere, for example. Doesn't have to be.
But if the physical one is not curved, the other ones can be curved. The ones that
the one that a non-physical system can live in any space.
No. Suppose you forget the theoretical sort of conceptual thing on that level. Your physical sample is flat, but you have flat coordinate system, flat distances, sum of squares.
Mhm.
But then you do canonical transformation to R primes
Mhm.
and express those differently in terms of R primes.
Mhm.
If you view it as a change in the metric, that metric can be non-flat.
This metric can be known delta ij, but the Ricci curvature is still
Which is,
zero.
that's what I'm
The,
saying.
the
it's Ricci
Riemann
flat.
curvature is still
It would be
zero.
non-trivial metric but flat.
Yeah, but
Ricci
with
flat.
no curvature. Okay, any question? Other question? Okay, so now it's curved. Yeah, I put it. Yeah, I can put my system this way to any system with any curvature. Yeah, it's a slight things that you have to think. Yeah, yeah. This definition make it sure that the system now that means that our system is invariant. The way that the system coupled to a gauge field is now is invariant under the following gauge transformation. So there is a gauge invariant. In a similar ways as the complex scalar field theories has a gauge invariant, this theory has a gauge invariant in which phi go to phi plus lambda dot. But now this G, Tij of R should go to Tij of R prime equal. So let me also put a prime here. The as a usual way. Prime Tij. No, the way around. Tij R. That's how the metric should transform. Okay, so now we can do linearization. So if I linearize, that means Gij equal delta ij plus hij. Also remember how R and R prime related to each other. R prime equal R plus R lambda, or R prime I equal Ri plus epsilon ij, some coefficient that I'm not going to write down. Do this. You find that this second equation corresponds to a change of Hij, which is, let me also write some, maybe the sign here is not correct, but something like this. Ij. You can do this. So sign can track. There is actually two derivatives acting on lambda, because in the canonical transformation, the displacement, just view about this contribution as a displacement of the coordinate contains one derivative of lambda, and when you do transformation of the metric, there is another derivative. So we are here, your metric changes by second derivative of lambda.
Suppose you wanted a magnetic field, just ordinary particles just move into the, Rx and Ry would commute. You could do a transformation, any transformation.
Without a magnetic field, you wouldn't have the dynamics. Purely in terms of R, you need momentum. So there is a P that come in.
But I could make a transfer. Okay, but suppose I make a transformation just on. I can transform RF, R into R, right? Some down the function.
right? But it's nothing here that going to be preserved. So all these assume that our system is a dynamical system with R being the only.
No, I guess the point is, if I want to preserve post-term brackets, real post-term bracket in R and P,
Mhm.
I can't just transform R non-linearly. I have to involve P.
Into P.
Yeah.
And that's, I'm not sure if that question has been explored. In general, we
I'm
have,
just wondering whether I can formulate that also in this kind of a geometric way of symmetry on the phase space, real phase space.
we have done that with the formulated theory. So in a recent paper that Luca de la Cretas and Umang Meta and
Okay,
yeah.
fair enough.
Yeah, we show that the Fermi liquid can be viewed using similar formalism.
Okay.
Yeah. Okay, so that's what so let's just recap what we have managed to do. We have managed to show that the system of guiding center coordinates can be coupled to external gauge field in such a way that there is exotic this higher rank symmetry. Yeah. So that's accomplished what I've set out. I've been able to connect the two things that we talked about in the previous lecture, the dynamics of the guiding centers and the symmetry. So now I want to explore the physical consequences of that new symmetry that we found. Can we get some consequence, some result? So I'm a practical person. Yes, the theory is good, but it's good if there's something that one can get from it. Okay, so now I'm going to show you how to relate, use this to relate two quantities. One quantity is the so-called Hall viscosity, and the other is the shift. So these two. I'm going to show that in a gap, quantum Hall system, the Hall viscosity is proportional to the shift, and I'm going to define the shift a little bit later. But the Hall viscosity, many of you probably have intuition about it. You see that appearing here. So what we are going to assume is that the system is gap. What it means to be a gap system? It means that at low energy there is no degree of freedom, no propagating degree of freedom. Boring, like an insulator. There's nothing in it. But that means that we can still integrate out all internal degree of freedom. Say, let's say pi for them. It's all degrees of freedom. And but my system, it's not a good psi. So psi, but the system, or is this? Let me call this R. I have that. Integrate over all this R. Assuming now I'm doing quantum theory. Sum over all trajectory of this R. My system also coupled to phi and coupled to H and J. And so the result will be a partition functions of phi and Hij, which I call the exponents of the effective action of phi and Hij. So this effective action, like quantum field theory with only background external field with no internal degrees of freedom.
Can you say what normally, if, our gauge fields, there are two situations, gauge fields have fluxes and don't have fluxes. So what is the meaning of that here?
that it
But
puts the
before you-
system in real curve space. Yeah, following the prescription that is done, that is the distance is measured on that curve space. Sometimes that is you do that, or sometimes you say the electrons, right? You can't do that to a magnetic monopole, but in principle, if there was a magnetic monopole, you can put it in a system and then ask the question, what is the physics of the electron in the field of magnetic monopole? Because it's consistent. You can do so here. You can also do that.
I mean, it's a helpful device to calculate correlation functions, I think.
Yeah.
But the actual sample, these are all flat. These are all gauge transformed.
Unless I do something to mimic this.
Right.
Yeah, and then I have non-flat system. Okay, so this effective action, I'm trying to find out what is possible. So my my ideal, or what I'm striving for, is a type of Chern-Simons term. So a Chern-Simons term is a term that usually the first example, the Chern-Simons term appear in +1 dimensional system with U1 gauge field. So let's recall the properties of that Chern-Simons theory. So this effective action in 2+1 QED with gauge field being just a mu of x is some kappa divided by 4 pi integral d3x x and t, and then epsilon mu lambda a mu d mu epsilon. So that effective theory, this Chern-Simons term has unusual properties that the Lagrangian this Lagrangian is not invariant, not gauge invariant. But the whole action is gauge invariant if up to boundary terms, which would be 0 if the fields are trivial at the boundary. So, but this whole thing is gauge invariant. So that's not what we are going to get, because we don't have the U1 gauge field. We have some more non-trivial higher rank gauge symmetry, but we still want to see how this would put such. We want to see if the Chern-Simons term is possible. Any question?
I'm confused when wherever you use the fact that you know the gap.
If the system has a gap, to be able to say that this effective action is a local functional of phi mh.
That's the only way you can figure out.
Yeah, otherwise you would get a non-local term. So one example is when you do that all the time is in insulator. Insulator have no degrees of freedom, and so when you couple that to U1 gauge field, you get E epsilon E squared plus 1 over mu E squared. So instead of the E squared minus B squared, like in the vacuum, the medium will correct the coefficient in front of this term. So that's still local in terms of E and B.
I mean, I could have, for any problem, right? If it wasn't quantum Hall, I just take a generic Hamiltonian. I can always make the Hamiltonian covariant, change all the distances with the Gij. and then I would still have this kind of gauge, this kind of symmetry just in the problem. But you're saying somehow here, this particular form will give us something interesting. Like this particular form, when we do the transformation, that we have an LG squared to partial of lambda, that's what gives us something interesting to say about all the viscosity and the shift and all of that.
So there are various ways. So this is just one way. The quantum Hall problem has a magnetic field going through it. So this magnetic field is invariant only under diffeomorphism that preserves the area. Yeah. Otherwise, so if you now try, so that's why this area preserving diffeomorphism appears.
And that restricts the form of this Hij transformation.
Yeah. And so, in the more general case, the this coupling of the metric to the system allow us to derive the conservation of energy and momentum. Here we see that momentum actually is not conserved because of that magnetic field, and so that corresponds to restricting the. It's related to restriction of the diff to volume preserving diff. So the Chern-Simons term is quite non-trivial. There are various things. So first of all, in 2+1 dimensional electrodynamics, this is a term with the lowest number of derivatives that is still gauge invariant. So that's the first thing. If its coefficient is non-zero, it's going to dominate the physics of long distances. Secondly, one can show that this coefficient in front of this term has to be quantized, but it requires certain extra consideration. So for example, the E squared and B squared, they all have two derivatives, but this one has only one. Yeah. But in our case, actually, we want to turn out that the Chern-Simons term here has also this Chern-Simons term there captures some topological properties of the state that we are describing, and here going to be this also another set of topological. Yeah.
So because you have an external magnetic field, you might expect that the effect factor brings time.
Yeah. Yeah. The fact that it has another thing that one can say is the following: if you write it as AI, there is term with only one time derivative. Okay? And term in the action with one time derivative usually correspond to adiabatic phase. So this term is also interesting from that perspective. They are all related to adiabatic phase. Doesn't depend on how fast the field changes. It just depends on the trajectory. Okay, so I'm trying to write down. I'm going to try to write down some term and see by try and error whether Chern-Simons type of term is possible here, and then extract the physical consequence if such a term exists. So here I want something that looks like AI dTij, but there is no, our gauge field has two indices. So the next best thing one can do is to write epsilon jk hij 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 dot. So that's a term that we are going to try. And now we can ask, what is the how this term transform under this gauge symmetry, that the transformation law that appear in one of this board. So it's a straightforward calculation. We just take variation, well, we just follow through the algebra, and then let me just write down you the answer. The answer we get is something like this: LLB squared up to a sign. Okay. Not sure how on the side, right? Hij dot minus Hij Eij lambda dot. Okay, so for first term come from the variation H, and the second term comes from doing variation of this H dot. So H variation of H is lambda, derivative, second derivative of lambda. So with all these epsilon tensor you have to do, and then use. Here I also use the fact, I also assume Hij is 0. But that's another thing that I have to do. Hii is equal to 0 is consistent with the gauge symmetry. Okay, so that looks promising, but it's not yet it's not clear yet how we can cancel. That's a, but if we can integrate by part, this, imagine that all this stay in the action, integrate, then we can integrate by part, decompile these two terms into one, because the time derivative can be pushed here and the spatial derivative put on the other side. So that becomes 4 LB squared. E IDJ let's write lambda dot EIDJ HIJ. So I push all the time derivative on lambda and push the spatial derivative on H. And now it's clear how to make this invariant. We have to add a term to cancel this. So the term that we need is something like phi dot, again with a maybe a minus sign, and then 4L minus 4LB squared, phi dot EI phi and EIDJ HIJ, because phi under gauge transformation give me lambda dot. So the goal has been accomplished. We find that it's possible. Following term is possible. It has to be integral over space. The Lagrangian itself is not invariant, but the integral of that up to boundary term is invariant, and the term looks something like this: EIDJ HIJ minus 1 over 4L B square something epsilon IJ maintain so the equivalency, the higher rank version of the symmetry looks like this. Okay. Use this order. What are the physical consequences from this effective action? Suppose I have some quantum Hall states, and then I integrate out degrees of freedom, and I find that there is no time reversal symmetry, and so that such a term appears. Can I interpret this term? So the second term, H here, H dot, correspond to the whole viscosity. See that by taking this, by computing the stress tensor, by differentiating the action with respect to H, right? And so you can find this is equal to summation A I A K times k j dot plus epsilon j k h k times dot with coefficient. Let me call this coefficient from your c, and then the coefficient will be c divided by 4. Some coefficient. So we have to do algebra to get the precise coefficient, but it has this form, the stress tensor equal to the derivative of the metric. So you imagine pretending that you think about this quantum Hall system as a fluid, changing the metric, like this H is the shear rate. Basically, this is Hij dot is a shear rate. And then the stress tensor is not in the same direction as the shear rate, but rotated 90 degrees. That's the whole viscosity.
Why do you not have a phi term? Like if you take the Hij derivative, I would move the derivatives onto the phi.
Yeah.
Why is that not in the Hij term?
That's actually a good a valid point. Actually, you get the following. Let me add some here term. You get something like this: dkvj plus djv. You can check that this derivative acting on phi can be rewritten by changing this h into a form that make the system even more like fluid-like. That's basically here, and vi is the drift velocity, epsilon ej divided by v, and ej is phi. You can do the calculation and see that actually this derivative acting on phi can be written as a shear, as a shear rate tensor. So the whole viscosity is directly related to this coefficient and the dimensionality. So this coefficient turn out to be dimensionless, I think, and the whole viscosity is just that dimensionless coefficient times LV squared.
From the point of view of the partial quantum Hall effect, that C somehow emerges from whatever this Lofton wave function or something like that.
Mhm.
That is a property of this gap.
That is the property
quantum
of
Hall
any
state.
gap state, yeah. And now, but this property actually, the coefficient C turn out to determine another quantity. That is the quantity that I call shift before. So to do that, let's compute another thing that is the density ds over d phi. Okay, so there are some other terms that we didn't take into account, but the contribution from this term is C di dj hij. But di dj hij actually equal to the Gaussian curvature of the system. And now I ask you to believe me that this is remain the Gaussian curvature even if we are going beyond the quadratic small h approximation that we have followed all the way. It's remained just a Gaussian curvature. So this coefficient C give us an additional contribution to the charge density. Usually in a quantum Hall state, the magnetic field determine the density. But if the system is curved, there is some correction proportional to the whole to the Gaussian curvature. So the term here is the usual B plus U over 2 pi plus B magnetic field relationship between charge and charge density and magnetic field. And now, but that's the usual system. Yeah. So now, if I integrate this, let's see if what happens if I integrate that over space. The total charge, and then equal to mu time integral over B over 2 pi. That usually called the number of magnetic flux, or the NB, number of magnetic flux. But here I have C time integral over R. That is the Euler characteristic of the manifold, which would be 0 for torus, but 2 for sphere. So what we found here is that there is a prediction that if you have some kind of a quantum Hall state, and we put it in, say, Laplace wave function. Suppose I do Laplace wave function on a torus, then I know exactly that the number of electron is 1/3 of the number of state on the lowest number of flux quanta going through the torus. But if I do the system on a sphere, and then there could be some extra. So one exercise that one can do simple is the nu equal 1, the integer quantum Hall state on a sphere. If the number of magnetic quanta through the sphere is equal to NB, then the spectrum of the Schrödinger equation on a sphere has NB plus 1 state on the lowest Landau level. Something that you can use quantum mechanics to do. But for Laplace state, that also can be done. That's called you equal 1/3 state, and you get some coefficient. So this coefficient is called a shift. I think it's usually written as a product of nu and the shift. This is called a shift. Equal to and for Laplace state it's 1/3. This shift is equal to 3. For example.
Numerical people like Edward often do fractional quantum Hall effect on the sphere. Do they know about this relationship? Does it? Do they take into account this?
They always have this effect. Sometimes they use it to select out, to improve the numerics, or to select out the state that they want. For example, we can try to get to, say, more rich state. We know the shift of that is 2, so we can just design the number of flux and the number of electron to fit that. Or we can just do the reverse and check that more rich state, the state that minimizes this energy has a correct shift consistent with the more rich. Things like that. It's always useful. It's rather useful in numerics. But
he didn't introduce G, but he got introduced simply by changing canonical transformation on R to R prime. Then the curvature would still be 0 because it's just a diffeomorphism, and it's a Ritchie metric would remain Ritchie flat, even though Hij would look non-trivial. So then shift would still be 0 consistently because you remain in the plane.
I would just say you don't get any constraint. You have to imagine that you can put the system on the sphere, and from the information that it's possible to put the system, you don't have to do that, but in your mind you say it's possible to put the system on a sphere.
But
The system is consistent.
Hij has to be non-flat.
It has to be non-flat, but the system we can put the system and preserve the symmetry, and that's enough. That allows you to relate. In this, it has to be from the center. So you imagine that you capture magnetic monopole from somewhere and put it in the center. Even on a torus, it's impossible to have a magnetic field through a torus without magnetic monopole. So it's again an exercise, theoretical exercise, but electrons can do that. So because we should say if we get the magnetic monopole from somewhere, electron would have any trouble living in this world. Yeah.
So I mean, you start with Hamiltonian, and you're saying if the state gap, then we're pulling out this S effect. I'm just trying to understand. Can one see that more explicitly from that form of Hamiltonian, or you just wave your hand?
I wave my hand.
You
Let's
wave
just
your
say
hand.
that.
Say this is the simplest action that could possibly come out as local.
Yeah.
and you know that this is the symmetry of the Hamiltonian and that must be the symmetry of that action.
Yeah. And then you get the
I accept that.
yeah, connection between Hall viscosity and the shape is known. I forget when, but not it's something that that wasn't seems to be trivial when it was discovered.
So the value of S is known for the various
It's known. Yeah.
fractional upon Hall state, people calculate.
Yeah, it's
So you're saying
rather
it's 3 for the.
yeah, it's rather straightforward. On a sphere, it was done by Haldane. He just generalized the Laplace wave function to sphere. One can do that. First, we have to construct some kind of it's basically constructing the wave function for the Van der Monde determinant, and then take the cube. Like it's exactly the same as Laplace did, but on a sphere. But the calculation of the whole viscosity of the Laplace state is extremely non-trivial because you have to follow the Berry phase of a multi-body wave function. And that is not something that can be done appealing to this plasma analogy that doesn't know anything about the phase of the wave function. So that's very non-trivial. But the result come out to be the same as one can get from this argument. So this is not the argument that originally was done to show the connection between Hall viscosity and the shape, but this is one of the ways to derive it.
Yeah, I'm curious about the role of the gap. So why the gap system?
Yeah, the gap allows us to restrict ourselves to terms that are local, like the one that we wrote here. Right? Otherwise, you can imagine H times H prime, but there is some kernel between them. There is non-local product of H in one place and H prime in another place. That would be completely difficult. It's very difficult to analyze.
And a simple example of that is if you have electrons in a uniform magnetic field, and you ask what's the free energy of that system. The electrons, then it goes like e to the 3/2 power. Just for dimensional analysis, work that out. So it's some, it's highly, doesn't have a simple polynomial expression.
Near b equal to 0, it doesn't have.
Right, it's
yeah.
singular, and then you have fluctuations in space. It'll have derivatives of 3/4 power and stuff like that.
What is E?
This is just a B field.
Oh, B.
Just a magnetic, electrons in a magnetic field. Yeah. And you think about the Hofstadter butterfly or something like that. It's just, you have all that non-analytic structure.
This can system will be like
No, his interactions are very long.
Yeah, it's just the description is restricted to incompressible space, gap states.
So, but it's highly non-trivial because, if you're in the integer Hall effect, then these interact trying to get all the states are filled. But if you're in a fractional Hall effect, physically the state is gapped, but that's in some, what should I say? You don't see that from the V of RA minus RB. You have to solve that problem to see that it's gapped. So it's not like, you can mentally appeal to the fact that the answer is gapped in terms of RA or B degrees of freedom, and so you can integrate them out. But actually carrying that out is not.
It's not easy, but this is the
not
thing.
possible.
Yeah, that's another thing that I think experience with quantum chromodynamics put you in a correct mindset. That sometimes it's impossible to derive, say, the pion from quark and gluon.
Yeah.
You can try to, it's very complicated, and at the end, nobody's going to believe you. But this pions, effective Lagrangian is very constrained from symmetry, like chiral symmetry. So similar things happening here. We just say it. Let's not pretend that we are powerful as we are as smart as Laplin, but let's try to just take what is known, assume it's gapped, and then see what comes out. Okay, hope it's useful. Yeah, thank you very much.
Any more questions?
Wondering if you could comment on the experimental observability of either of these, and also on the quantization of Hall viscosity. Because I mean, all of this is classical, but people say that there are statements that the Hall viscosity is quantized, like just like the Hall conductivity.
Actually, the statement that it's quantized, I'm not sure I understand very well. We observe that this, at least for the simple state, this S is always integer. I'm not sure I can. Let's say it's like the number of state, the number of charges on a sphere has to deviate from that by an integer. For example, that some,
Hall viscosity is not a quantized object.
it's quantized up to this magnetic length. Yeah. So, but after you factor out this magnetic length, the value is for quantum state seems to be just some, at least a simple fraction of some. So it's quantized at that level. It's all quantized.
Is there an understanding of why why this number and the C are
Quantized?
Yeah, why is that quantized?
I don't have this. I haven't seen the a formula. So for whole conductivity, there is this formula that relate that with the integral over the Brillouin zone, and that has to be integer. I don't see similar things here.
So then, like, if that's
But but that formula doesn't work in fractional quantum Hall state. Right? So yes, the
so are you saying so then is the statement that when people say the Hall viscosity is quantized, is that an experimental fact? Is that like
no, it is coming from here. I think that this relationship with the shift. And the shift, you can see it's related to the discrete number of particles, and this it is discrete. Yeah, so chi has to be 2, 4, etc.
BS is the C that's up there, and US is the C that's up with the Hall.
Yeah, nu s is that C.
I see.
Yeah.
But and then if you have a number in front of the C, that's just a constant.
That's
not
like
a quantity.
4 or something. I didn't compute, but it's like 2 or 4 because with differentiating that you get sometimes 2 from
But it's
2
not a
different
physical
terms.
parameter, it's just a factor with a
Yeah, it's just some number, some simple number, 2 or something. Yeah. Is that usual way? Coupling what to curve space?
Dipole symmetry.
Dipole symmetry. Dipole symmetry is a is like a global version of that. So so you see here this symmetry here, for example, you can do. So for example, you can shift R by a constant. Shifting R by a constant correspond to lambda that is linear function of space. That's the dipole symmetry. Dipole symmetry correspond to shifting all the to a yeah. So you can ask the following question. So yeah, everything I did here is fine. But suppose I don't want the metric to change. I want to restrict myself to symmetry that are real symmetry of this without introducing the metric. What can I do? I can shift R by a constant, for example, shift all of that. How I do that? I restrict this lambda to be a linear function of space. And that chart that generates that is integral of x times rho. That's one symmetry that you see. Another symmetry, you can rotate this R rigidly in space. And again, you can check that this corresponds to lambda, that is x squared. And that's related to the conservation of integral of x squared times rho. So here it's all the symmetry are very.
That's a global component.
Yeah, that is global components. Yeah, you can do that without introducing metric into the system.
One more.
Good, sorry. Could you comment on the observability and experiment of either of these effects?
Okay, so this is a subtle question. So, yeah. In order to observe this whole conductivity, the easiest experiment, the most straightforward experiment one would do is to scatter gravitational wave on the system. Okay, so suppose you can do that, right? You just scatter gravitational wave, and then you can get response.
Put it in orbit around the ball.
Yeah, but usually you cannot do that. And so what you can do, the next best thing is to use the photon. So graviton has spin 2. So the thing that you can do is to have photon coming in with spin 1, and then you observe spin -1 coming out. So you give the system something of spin 2. That experiment is the polarized Raman scattering experiment. And you can, if this is the next best thing one can do, yeah, and you can convince yourself that it can observe at least the sign of this, and the good condition you can find the sign of the whole viscosity.